Hello students, I am Dr. Tanmay Vishwash. I welcome you all in my channel Chemistry the Mystery of Molecules. Today's topic of discussion is a very interesting name reaction, that is Fleming Tamao oxidation. And by the way, this topic belongs to asymmetric catalysis, and that's why this reaction produces alcohol which is enantiomer. Okay, so in this today's discussion we shall discuss this oxidation reaction with the basic concept, mechanism and examples with one MCQ. So before going to details, the MCQ is in front of you. What is the major product of this reaction? So you can see this reaction. I request you student, please pause the video, read the question carefully, try by yourself, and whatever answer you get, please write in the comment box. Don't hesitate whether your answer will be right or wrong, because self-evaluation is essential for improvement. And don't worry, at the end of this discussion, you'll have the right answer with explanation. Now let's go back to the main topic, that is Fleming Tamao oxidation. In some places you can say Tamao Fleming oxidation. So actually these two are the name of two scientists. Now actually what is new in this chemistry? Here first you may consider this alkene could be asymmetrically silylated by hydrosilylation procedure, and this catalyst is actually student asymmetric catalysis. So one side hydrogen addition and another side silicon addition. So in this way this is the hydrosilylated product and this is the asymmetric center. Now oxidation of this silane or carbon silicon bond, so this is carbon silicon bond, results in this asymmetric alcohol. So this actually may consider this asymmetric silyl compound could be oxidized to the corresponding asymmetric alcohol, and that is the uniqueness of this reaction. Now a simple question, why oxidant is needed? Simple, we know that silyl ether, silyl compound could be hydrolyzed or deprotected using fluoride. It's true, because this silicon fluorine bond is significantly stronger, and by the way this should be fluorine. So stronger because of means d pi p pi back bonding, means vacant d orbital of sulfur as silicon forms a back bonding with the filled p orbital of fluorine. So that's the thing, fine. But in this case, are we getting alcohol? No, this is hydrogen. But in order to get alcohol, oxidation is essential. Okay, so that is the uniqueness. So, and if you look at the polarity of this bond, this carbon is delta negative and this silicon is delta positive because of electronegativity difference. So if you hydrolyze this simply, then this hydrogen is expected to go here and OH will expected to go silicon. So you will never get the final alcohol by direct hydrolysis. For that purpose you need oxidation, and that's why this is Fleming Tamao oxidation is utilized. Okay, so in presence of oxidizing agent, these bond oxidized and ultimately produce this asymmetric alcohol. Okay, so what is the main reaction and the basic difference? Actually this reaction belongs to two different reactions. One is Fleming oxidation, which is associated with less reactive substance like phenyl dimethyl silane, and this part is asymmetric. Fine, please remember it is oxidized and ultimately produces this asymmetric alcohol. And by the way, same alcohol could be produced using Tamao oxidation, and in this case there is an X. This phenyl group is replaced by this X, and this X is heteronegative, means heteroatom or hydrogen. So you may consider that this Tamao oxidation condition or this substrate for Tamao oxidation is relatively more reactive compared to the Fleming oxidation substrates, and that's why you see when you want to carry out this Fleming oxidation, first it converted into a reactive substrate, later on it is oxidized. So we shall learn everything step by step, but before going to details, let's learn about the first reaction, that is Tamao oxidation, where the silane is converted or oxidized using hydrogen peroxide as oxidant and potassium bifluoride as fluoride source, and you can see DMF as a solvent, and the reaction condition is pretty mild, 0 to 60 degrees centigrade is enough for that. Okay, so if you look at the mechanism, what happens here? First, fluorine attacks the silicon center. Why? Because silicon has energetically accessible vacant d orbital, and silicon fluorine bond is very stable because the this fluorine silicon, because you can see the fluorine has vacant p orbital, means 2 electron, and this silicon has energetically accessible vacant d orbital. So filled p orbital of fluorine will donate electron density to the silicon atom, means that this single bond of silicon fluorine is not a perfectly single bond, it has some partial double bond character, means more stable bond, and that is the driving force for silicon fluorine bond formation. Please remember this chemistry in case of silicon, this is very important. Now, so first fluorine will attack, and after this attack the adduct having 1 unit of negative charge. Fine. So in the next step what happens? Hydrogen peroxide act as nucleophile and attacks the silicon center. Why this hydrogen peroxide attacks? Because the lone pair repulsion on hydrogen peroxide is called alpha effect, and because of this alpha effect hydrogen peroxide becomes a better nucleophile, so it attacks the silicon center. Fine. And we know silicon can extend its coordination number because of that energetically accessible vacant d orbital. So from 4 coordination to right now silicon is 6 coordinated. Fine. And after this attack of this hydroxyl, this oxygen will have a formal positive charge, and in order to remove that formal positive charge, proton will be eliminated, minus H plus, and ultimately the complex will be di-negative anion, or this hexa-coordinated silicon species. Now, student, please recall the Deakin oxidation, Beer-Villiger oxidation, etc., where we have observed that migration of alkyl group. Okay, here the same thing, means my carbon atom will migrate with its bond pair, and these means this total migrate on this oxygen, it will leave. Why? Because the oxygen in hydrogen peroxide having oxidation state -1, so it want to get reduced to -2 oxidation state, and because of this lone pair repulsion, the oxygen bond is not that much stronger. So that's why this reaction will occur, and ultimately this alkyl group will migrate on the oxygen. And student, whenever you do any migration drawing, please try to keep everything as it is possible and only change which bond is broken and which bond is made. In this way you can reduce the chances of mistake. Now, so here actually student, the oxidation happens, mean the carbon silicon bond got oxidized into carbon oxygen bond, means this bond. Okay, and later on hydrolysis here will ultimately result here this alcohol. So that was the target. So this is the overall mechanism for Tamao oxidation. So next, the Fleming oxidation have a similar concept but little different. So let's learn what is the difference. Now before going to that, reaction condition of Tamao oxidation. So actually this oxidation could be carried out in 3 types of condition: basic condition, acidic, or neutral. Now why this is basic? Because sodium bicarbonate is used here. Now why acidic? Because acidic anhydride. Actually acidic anhydride is a neutral molecule, but see here 30% hydrogen peroxide is used. So 30% is hydrogen peroxide. What is the 70%? So here 70% is water, and these water reacted with acidic anhydride to produce acetic acid, and that's why this is acidic condition. And another is neutral condition, where you can see hydrogen peroxide KHF2 just some time before we have discussed. So actually all 3 oxidizes this corresponding silane to this alcohol, but condition is slightly different. And remember student, when we do such kind of catalyst, we need to take care of what other functional groups are present in the molecule. So based on that we choose whether we shall go acidic, alkaline, or neutral. Now let's discuss this Fleming process. So in this Fleming process, this silane is converted into the corresponding alcohol, and this Fleming process is divided into two methods. One is 2-pot sequence and another is 1-pot sequence. What is the 2-pot sequence? Here this phenyl dimethyl and this is alkane and silane alkyl group first reacted with HbF4 and ether or BF3 acetic acid. So what it produces in the first step, I am writing here. The first step is, you can see this is fluorine, this is silicon, these are two methyl groups, and finally this is the R. Okay, and these will be oxidized in presence of this m-CPBA, meta-Chloroperoxybenzoic acid, triethylamine water, or m-CPBA, potassium fluoride, DMF, ultimately produce the final alcohol. Okay, and what is the one pot? One pot version is mercuric acetate, paracetic acid, and in acetic acid medium. This is one method, and another method for one pot reaction is bromine in paracid or KBr in paracid. Okay, so these are the two methods. Let's discuss everything step by step. So how the two pot solution reacts. So first is reaction of BF3 and acetic acid, and by the way student, this BF3 is actually Lewis acidic. We know 6 electron species, and acetic acid acts as a nucleophile. So this acetate anion attacks this BF3 group and ultimately produces this part. Okay, this BF3 acetate, and it along with that it produces one molecule of H plus. Okay, that H plus act as electrophile, and it is responsible for this ipso substitution. Fine, it attacks. So ultimately after canonical form, the positive charge goes to the para position, because in first place the charge is actually student this ortho position. Everything is same. This is the silicon and this is the proton, and in the next step this bond comes here, so positive charge goes para position. Fine. In the next step what happens? This tetra coordinated boron, which has a formal negative charge on it, shifts fluoride from here to this fluorine attacks silicon. We know silicon fluorine bond is very stable. Consequently what happens? This carbon silicon or phenyl silicon bond got broken, so it goes, this comebacks, and in this way it produces these fluorodimethyl silane. Along with that, what is produced here? Along with that, in this case it produces this fluoro derivative. Okay, now it got oxidized to produce alcohol. Now this mechanism, I guess you are very much familiar, because sometime before I told that is Tomao oxidation mechanism, similar. Now what is about the one pot reaction? One pot reaction, if you look at here, mercury acetate is used. Now student, what is the difference between H plus versus Ag2 plus here? Because we know carbon center means carbon here acting as a nucleophile, and carbon is actually softer in nature, but proton H plus is harder in nature, whereas mercury is also softer in nature. So that is the uniqueness of mercury. So mercury does the similar ipso substitution, and ultimately it produces this similar ipso substitution compound similar way, and here instead of fluoride, this acetate anion from the mercuric acetate act as nucleophile and attacks this silicon center, and in this way reaction happens, and ultimately it produces this acetate attached silicon, or you can consider heteroatom attached silicon derivative. Under similar reaction condition, means paracid acetic acid, it produces the alcohol. So this is the strategy for the actually Fleming oxidation reaction. Okay, so based on this understanding, a simple way, very easy way how we can propose the mechanism for Fleming oxidation. So this silane derivative got oxidized with paracid. So what happens? These lone pair of paracid, similar thing student, just remember what I told some time back, this alpha effect, lone pair repulsion make them better nucleophile. So what it will do? It will attack the central silicon atom. Okay, because silicon can expand its coordination number. So fine, first attack is happen. Now in the second step, here student, a very interesting reaction is there. Actually it's little complicated, like these proton got abstracted by this carbonyl oxygen, point number 1. Second, because after this nucleophilic attack, this oxygen will have a formal positive charge. Now in the second step, this alkyl group migrates with retention in configuration here, and this comes here. So this bond opens and it abstracts this proton. Okay, so this is the overall mechanism, and in this way what happened? just oxygen silicon bond. So this is actually the oxidation state, and then workup will result in this final alcohol. So this is the mechanism of Fleming oxidation. So both mechanism resembles quite so now what is the evidence for retention in stereochemistry? Because we are saying that groups are migrating with retention. What is the evidence? So if this Tamao synthesized following norboryl silanes, subjected them to m-CPBA. So m-CPBA is oxidizing agent. So if silicon is here, means exo isomer 100%, then we know this bond will be oxidized. And student, a same easy process, just as tricks, what you will do that under this condition, if you similar condition, what it will do, just put a OH in between carbon and silicon. So this is the tricks, put a OH. So in this way we will get the final product. Now just look at under this condition m-CPBA DMF, this 100% exo isomer is produced from exo. So this proves the retention. Not only that, this 95% endo isomer is produced. Just as for our tricks, there will be alcohol. So here alcohol is produced, 95% endo isomer. So these two example proves that this reaction proceeds through the retention in stereochemistry. Means the migration of this alkyl group is associated with retention in configuration. Now let's go to little difficult thing, student. Just listen little carefully. Previously we have discussed easy thing. Now alkynyl silanes have different reactivity than alkyl silanes. So this is the tricks. So you take this alkene silane under neutral or basic condition, what it produces? It produces this aldehyde. Now what tricks I told? Whenever you see a carbon silicon bond, you put OH. So this is OH. So this is the product. Now we know that this is actually a enol, and enols are relatively less stable compared to their other counterpart, that is keto. So you can expect that this is R. So this is double bond O aldehyde. So ketoenol tautomerism. So this much we understand. This is very the basic one. But now in acidic medium things changes. Means in acidic medium over oxidation happens, because we know aldehyde takes 2 unit, removes 2 unit of electron, means 2 unit oxidation of aldehyde results in carboxylic acid. So from this thing you can understand that for first one, if 1 equivalent of m-CPBA needed, and for the second one means here 2 unit needed in acidic medium. So that is the thing here. But if you take this silane, this is a substituted silane, or you may consider in this case the secondary carbon silicon bond is secondary. So just as our tricks, we told that this is R double bond, this is R prime, this is OH. So through ketoenol tautomerism, what it will produce? So this. Now under acidic, neutral or basic, if you take any medium, ultimate product is here ketone. But in the previous case, you see here aldehyde was oxidized into the corresponding acid. Question 5. We shall discuss this thing in the next slide. Now how this aldehyde got oxidized? See, in presence of oxidant, what happens? First, this part is converted into OSI. Okay, this enol ether. By the way, you may be confused that, sir, how this reaction happens. I shall give you an example after some time, where you can say first oxidant, or in this case you can consider m-CPBA, will result this silicon enol ether. Means this is actually a alkene silane, and this part is silicon enol ether, because OSI, this part is there. So I have already discussed many lectures on this topic, so please visit for better understanding, and later on it will undergo hydrolysis and produce this aldehyde. Now this much part is enough. I guess you have understood. By the way, this is a very simple way for presentation. Actual mechanism I have taught you before some time. So in presence of acid, what you can expect, that it will undergo protonation. and in the next step means after this protonation, these aldehyde carbonyl will become more electrophilic because of this protonation. Then this m-CPBA, okay, we know this m-CPBA, this oxygen is acting as the nucleophile, okay, so it will attack here and it will open up, so this intermediate will be produced. Now in the next step what will happen, that you can see that these proton will be abstracted by the base, okay. So what it will do, so if this proton is abstracted, so this bond will come here, push, and here it will leave and it will go. So this is actually, student, the oxidation step, and in this way aldehyde is converted into the corresponding carboxylic acid. So this is the 2-unit oxidation, simple thing. Now question is, why in the case of ketone it didn't undergo oxidation to any carboxylic acid? By the way, remember student, aldehydes undergo oxidation because of these hydrogen, means aldehyde hydrogen are CHO, these hydrogen, but ketone do not have these hydrogen, instead of they have R, so breaking of this carbon-carbon bond is difficult. So that's why ketone do not undergo oxidation that much easily. And by the way, I have already discussed 2 lectures, that is oxidation of ethanol to acetaldehyde and carboxylic acid, and oxidation of tertiary alcohol to corresponding other derivatives. So please visit these 2 lectures, it will help you to clear the concept why the oxidation of ketone is difficult but oxidation of aldehyde to the corresponding carboxylic acid is easier, okay. So now let's discuss another topic. So if you take 3 equivalent, first 1 equivalent results in aldehyde, 2 equivalent results in carboxylic acid, first aldehyde then carboxylic acid, and right now 3 equivalent m-CPBA, what it produces, aldehyde but 1 carbon less, okay. Actually there was 2 carbon after this R, but right now 1. So why this is happening, what extra m-CPBA is doing and how doing? So if you look at the mechanism, first is silyl enol ether formation, I have discussed, and if you want to know little more in details, so this is m-CPBA, same thing, it produces first epoxide, later on in presence of B, this is actually a Lewis acid, it produces this silyl enol ether. And by the way, if you use m-CPBA, actually reaction in the reaction medium after oxidation, what it will produce, it will produce meta-Chlorobenzoic acid. So under this reaction medium, this epoxide opening will follow the acidic pathway, means acid mediated epoxide opening, and ultimately it will prepare the similar one. I give you this home task, please write the mechanism by yourself, okay. So it will produce, now we have understood this. Now in the next step what you can expect, that in the next step this it will be converted into this m-CP, using m-CPBA it will be converted into this first enol. Actually this is actually enol ether, in presence of m-CPBA this enol ether will be oxidized and oxidized into the corresponding alpha hydroxy carbonyl compound. Student, this reaction is also a very important reaction named as Roux-Bottom oxidation. I have already uploaded a dedicated lecture on this, please visit this video, I have explained details there, I am not going to explain here because the lecture will be too much lengthy. Now in the third stage, using m-CPBA means third equivalent, what it does, these m-CPBA just reacts as usual, means nucleophilic attack on this carbonyl, fine, everything is fine, but here the twist means previously hydride was abstracted or migrated, whatever you say, but in this case this carbon-carbon bond, means I am talking about this carbon-carbon bond, not the double bond, right now this is the single bond or sigma bond, these carbon-carbon bond will migrate, so here in this way, so what it will produce, you can consider this is a acetal type I say, because one carbon oxygen single bond, another carbon oxygen single bond, acetal ester because this part is an ester type, and we know these acetal are not stable in acid, and after this peroxy reaction, means peroxides or peroxy acids are converted into corresponding acid. Here this meta-Chlorobenzoic acid, this acidic medium acetals are not stable, so they undergo hydrolysis and produces these aldehyde. And by the way, I have already discussed about the acetal hydrolysis in acetal hydrolysis and preparation, so please visit if you have any difficulty in understanding. Now, so this we have understood. Now another interesting concept, that is contribution of steric effect. Why this is important? Actually, we are converting or oxidizing these asymmetric part into the corresponding alcohol. Now why do we need to consider the steric part? See, if these three R groups, if this means these are groups attached to this carbon, they are too much bigger, then what will happen? These bulky groups will introduce the steric hindrance around the silicon center, and that's why nucleophile or oxidant, for example either this fluoride or hydrogen peroxide or m-CPBA, cannot approach to the silicon center, and it results in no oxidation. So that's why student, please remember, this bulkness is also an important. So you can see this isopropyl or this derivative, fast oxidation, moderate this tertiary carbon, but when these very slow, when this carbon is very slow, means 2-phenyl 1-tertiary butoxide, then reaction becomes very slow. So that is the thing we need to be careful, because increasing bulkness will reduce the steric hindrance or steric obstacle, such that reaction cannot happen. Now, so let's come to the example. So here we shall discuss 3 examples. Now here I shall focus only our point of interest, that is this oxidation. So this is the point of interest. Here you can see this is the silicon carbon bond, and as the tricks, this carbon silicon bond will be replaced by carbon OH bond. So you can see this OH. So this is the trick. So gone everything, and condition same, 30% hydrogen peroxide, KF, bicarbonate, methanol, THF, means basic medium reaction. It will produce this one. So this is, student, you follow these tricks, but first read, then follow this. Now second example, second point of interest is this one. Why? Because here you can see this carbon silicon bond, so it will be oxidized, and this is also base mediated, bicarbonate is there, and it will produce this hydroxyl. And by the way, a simple question, if you use acid mediated pathway, what will be the problem? Because see, this is actually a tertiary alcohol, and we know tertiary alcohol can produce carbocation very much efficiently if the medium have slight amount of acidity. So that's the reason why chosen this basic medium for this chemical reaction. Now let's come to the last example, that is this Pramacin. It's a natural product preparation, and here the main interest is, you can see this step. Okay, what happens? This carbon silicon bond is oxidized. Okay, and here it is oxidized, and m-CPBA is used as an oxidant. So what happens? Selectively in the top side, this carbon silicon bond was replaced by carbon OH bond. So this is the third example. Student, I am not going very much details, because I know this lecture is already significantly lengthy, and this condition, you see, it's a mild condition, significantly mild. So in conclusion, what you have learned today, that this is a relatively easy and milder oxidation reaction to convert carbon silicon bond into carbon OH bond, but asymmetric retention in configuration. And Tamao's oxidation is associated with one more reactive silicon center. In Tamao case, that is attached to heteroatom. So it's where at least one electronegative heteroatom is attached to silicon center. Now second, Fleming oxidation start from relatively less reactive silanes like phenyl attached with no electronegative atom, but in the next step, what happened? During this Fleming oxidation, the reactive silicon species is generated by ipso substitution on the aromatic moiety. Okay, and in this case, the stereochemistry of the migrating group is retained. So that's the most interesting point. Now let's come back to the MCQ. So reaction of this alkene silane, trimethyl silane, with this is actually acetonitrile oxide. Okay, this is an acetonitrile in oxide, you can consider that type acetonitrile oxide. What is the product? So let's learn the mechanism. So what happens actually, you may consider this is a 3+2 type of cycloaddition. What happens, these bond you can consider that it can this bond can attack this silicon center, okay, and later on it will attack here and it will go. So ultimately it will produce this. And another interesting point is that, see, these two groups are in syn position, same side, so they will be same side, and silicon will go to the opposite side because this another bond formation, this silicon oxygen. Okay, so this. Now what is the answer of today's problem? So answer is this one. Okay, so this is the answer. Now question, why not other option, or if this question given to you, how can you solve this problem less than 30 seconds? First of all, you need to understand it's a cycloaddition type reaction, and in this case, student, so this is a 3+2 type. This oxygen will prefer to attach to the carbon which is closer to this silicon atom. Fine. And second thing, so it will produce a 5-member ring. Now epoxidation is not possible by this reagent. This reagent is actually dedicated for this 5-member ring formation. I have already discussed of another MCQ, you may visit. Now second thing, in this case these two atoms are in same side, so ultimately in the product they will remain same side because it's an actually this you may consider the cycloaddition type reaction, so their geometry will not change. Now if you keep this information in mind that it will be in same side, which option this is given? Option B and option D. So either B and D rest to gone, because here silicon and carbon, this carbon and this carbon got anti, so this is gone. Now this reaction happens on this orientation, means oxygen goes closer to this silicon attached carbon, so this is gone. In this way we will have the right answer. Okay, so this is the end of the discussion. I believe this video may be useful. I'm sorry this lecture is a little longer because but I wanted to cover or complete the whole topic in one lecture. So if possible, please visit my another channel. Thanks for watching. See you in my next video. Bye bye.